So I should apologize in advance if this is too basic for a lot of the audience. This is going to start very, very low, so trying to motivate why we want to do this kind of approach and what this approach is going to buy us in general and what the general methodological principles are. I'm not going to have a lot of time to dive into math. I'm certainly happy to take whatever questions you want, and please feel free to interrupt as I go if there's stuff that's not clear. So what I want to focus on is solving inverse problems with Bayesian inference. And I realized walking down here this morning that I don't actually have a slide that says what an inverse problem is, right? So generally an inverse problem is something where you have some kind of forward scientific model, as it's known, that models the universe, say like Chirag was doing yesterday, based on some parameters. And then the idea is from that, you have a way of simulating something that looks like your data, right? But what's really happening is you're observing data in the real world and trying to do inference on the parameters. So for instance, we might have, in the simplest case, going back to like when people were looking at gravity, Galileo built a ramp, right, to try to figure out what the gravitational constant was, and dropped balls on it and measured how long it took with this crazy water clock contraption for balls to move across different positions on this giant like ramp. So it's like a high school physics exercise, right? But the idea there is your measurements consist of this water clock actually looking at the data, it actually measuring how long something takes, and then the physical model was just Newton's. Well, was it Newton? No, I don't even think it was Newton at that point. So, sorry, my history of physics is not very good, right? Right. So, anyway, we're going to go on to talk about some actual inferences here. So, I want to talk by saying, why do we want to do this? Why do we want to do something like statistics? And largely, it's because uncertainty permeates a lot of what we do. Right? And in particular in statistics, we tend to break uncertainty down into three different kinds of uncertainty that we have when we're done. One is sampling uncertainty. That is, Galileo, when he did that experiment, only did it a finite number of times. He dropped the balls a few times. He didn't have infinite amounts of data. The data is finite. Right? So that introduces some uncertainty in terms of sampling. If we're polling somebody in a population about their attitudes, right, the fact that we only sample a subset, right, leads to sampling uncertainty. Our sample of people might not be representative of the whole population. So we get uncertainty there and extrapolating from a small sample to a larger population, right? The second kind of major uncertainty we have is measurement uncertainty, right? If I point a telescope at the sky and measure the angle, right, there's going to be error in that angle measurement, right? And I need to account for that angle and the error measurement in my model. And largely what statistics is going to do in inverse problems, and this is going to do, is going to give us a way to couple a scientific model and a measurement error model. The sampling uncertainty is sort of going to come in the background for free, right? The third thing that I think people often don't like to talk about in Bayesian statistics or other statistics is modeling uncertainty, right? So the idea is we're going to be applying some kind of model of whatever we're doing, a model of climate change, a model of gravity, whatever, and our model may not be perfect, right? It's like the Newtonian model of gravity was perfect enough for Galileo's experiment, but our models of voting preference or our models of the spread of COVID through the population are very, very imperfect and very approximate, right? So we also have modeling uncertainty that comes in, right? And I like this quote from Bill James, which says the alternative to good statistics isn't no statistics, but it's bad statistics, right? You may not think you're doing statistics if you're counting numbers and things like that. Ironically, Bill James wasn't actually a statistician and did really crazy stuff. So it's weird that he's the one who said this. He was a baseball, but still is, baseball stats guy. So probability and statistics, I think this is very confusing for outsiders coming into the statistical world, because probability theory is basically about using math to quantify uncertainty, right? But there's a lot of different ways this gets ramified into how people practice statistics, right? I'm going to be talking about Bayesian statistics, and I'm not going to spend a lot of time contrasting this with other alternatives. The idea of Bayesian statistics is we're just going to take probability theory the way it's written and we're going to apply it to everything we do. We're going to apply it to our data analysis. We're going to use it for prediction and forecasting. We're going to use it for model evaluation. We're going to use it for decision theory. And everything's going to have a very natural probabilistic interpretation, right? And you'll see that later as we go along, right? And since we're here at CCM, right, what are we wrestling with? What do I wrestle with on a daily basis? Well, I'm going to present a very beautiful picture that presents a very difficult math problem, applied math solving problem. So the computational bottleneck here is a couple different things. One is trying to figure out how to actually express your model. So a lot of what I do personally is work on probabilistic programming languages that attacks the first problem, right? I also work a bit on posterior inference, right? The problem that, and Dave's also going to be talking about inference problems in the next talk, right? And this is the problem of doing the computation for Bayesian statistics, right? Actually trying to figure out what your data implies. And I'll show how some of that goes and hopefully be able to make some comments on why it's hard. But like I said, I'm not really going to be able to get into like a lot of detail here. So as far as probability and thinking about probability, this is something that's very conceptually difficult. And I generally don't like when talks start with something like the philosophy of science, because usually that means you don't have enough content and you're trying to like backfill. But I think in this particular case, right, I think it's worth thinking about what probability is. And in particular, it's worth thinking about the Bayesian notion of probability. And before I say this, I should say that there's really multiple camps of Bayesians, right? And they don't all exactly believe the same thing about this, but I think the world is kind of converging toward this pragmatic notion of Bayesians, and the purely objective Bayesians and the purely subjective Bayesians are kind of fading into the kind of theoretical background as people like try to solve real problems, right? So this is actually from 1880s when John Stuart Mill was trying to figure out what induction meant. How do we go from data to theory, right? And this is following along from comments Laplace had originally made about Laplace, what's called Laplace's demon, right? But I think Mill said it better, right? Which is that we're not thinking of the world itself as being uncertain. Like maybe it is at some quantum level, but in terms of our probabilistic model, we're really not thinking that there's more than one gravitational constant out there. We think the world is what it is, right? Just like every other kind of statistician does, right? And if I'm looking at like what's going to happen if I throw this thing up in the air and catch it, well, I might be able to predict what's going to happen. If I knew everything about physics and everything about my physiology, you would have been able to predict whether I could catch this thing throwing it up and down. But in fact, we don't have all that information ahead of time. So the events themselves are certain, right? But probability, at least as conceived in a Bayesian setting, is epistemic. That is, it's about our knowledge. It's how much do we know about the world, not a property of the world itself. That is, we can't go measure something and say what its probability is, right? It's really characterizing our cognitive uncertainty in this, right? And people like to sort of pejoratively talk about that as if it were characterizing individual beliefs, right? But generally, those of us who do Bayesian statistics thinks it's just scientific knowledge. It's just how we encode our scientific knowledge into our models, right? So in some sense, that is a belief. It's a collective belief of a bunch of scientists, or maybe, you know, your own hypothesis. But it's not like, oh, I believe in Santa Claus kind of things. It's not, you know, that kind of belief, right? So let me try to make this concrete. Let's say we're talking about, I went to grad school in Edinburgh. It rains a lot there, right? If I ask you, what's the chance of rain in Scotland? If I don't tell you what day it is, right, then 52% is the number of days that it rains in Edinburgh. I think that's actually low. If I know the month is October, say you tell me, right, what's the chance it's going to rain someday in October? Well, that's 55%, right? If I know it's 24 hours from now, but you don't tell me anything else except that this is 24 hours from now, it's in October, so it's 55%, right? If I also have today's weather report, like let's say I know if it's raining today or sunny today or what the meteorological trend is, my estimate might go up to 80%. Right? If it happens to be the day and it's raining outside, then it's like 100%, right? And the point is the world doesn't change here, right? The world is going to rain, it's not going to rain, but what's happening is I'm getting different knowledge. I'm conditioning these inferences on different bits of knowledge, and how much knowledge I get to use to draw my inferences depends on how sharp an inference I can actually draw here. right? So coin flips are exactly the same, right? You can think of a coin flip going up. You don't, we can't predict, like at least a human can't predict what's going to happen. Somebody really good, a really good physical model could probably, look at that coin flip and figure it out. We'll probably get there eventually, be able to do that. In fact, I expect DeepMind to be able to predict coin flips from physics soon. So I like to start technical stuff with thinking about just the very simplest case of coin flips, mentioning coin flips. But now we're going to do something different. It's baseball playoff season, which is keeping me up at night. But let's say we have somebody with a true 30% chance of success, right? You don't have to think about baseball. You could think about what's the chance that a drug is going to improve the blood pressure of a clinical trial patient, for instance, right? Could be your 30% number. Right? What I want to try to get across with this is just how uncertain binary data is. So let's say I do 10 observations, right? And what I've got here is just simulations, right? So those numbers under 10 at-bats is the simulation of 10 trials 10 different times, right? So the first time somebody did 10 trials and got 1 success, right? At some point, somebody got 6 successes. Right, this is where you hear the announcers start saying, oh, they're trending, they're streaky, they're whatever. And you're like, with 10, you know almost nothing about binary data. Right, our estimates, if we just estimate the fraction of how many people have success, are going to range from 0 to 60%. I used a baseball example because we know nobody is better than 40%. Well, nobody's better than like 50% at this, right? And this person's, fairly low. Like I don't think there's been anybody who's had higher than like a 50% or maybe 50. I used to do this with batting average, which is a bad example, but I knew the numbers better. So we know that a lot of these estimates for small data are going to be very unreasonable because we know the range of like professional abilities, right? We may have tested a previous blood pressure drug and have a very good idea that, this isn't going to cure 99% of the people and it's going to cure more than 1% of the people. So we're coming into these trials with some more data than just these numbers. But even when you go up to 100 trials, our estimates look like 22% to 33%. Now, intuitively, 100 binary trials, like as a person, you really feel like that's giving you a lot of information. I do, doctors do. They go and make decisions based on seeing not even 100 patients. And they're like, in my experience, this is what happened. And this is the level of uncertainty that amounts from that, right? By the time you get up to 1,000 trials, this is something like 2 full seasons, right? Now you still have uncertainty that's in the 30% range. It's huge still. Even 10,000, this would be an entire player's career in baseball. We're still getting 10% levels of uncertainty, right? The reason I want to stress this is there's only so much we can get out of data. There's only so much certainty we can extract from noisy measurements, from binary data and things like this. And part of what statistics is about, in fact, largely what it's about, is characterizing our uncertainty from only seeing a small amount of data and having some kind of limited theory of the world, right? So let's talk about Bayesian inference. So we'll do a little bit of math, at least to set up our notation. And I'm afraid I'm going to have to assume that people know what probability densities are and things like that to get started. I'm not going to be able to give you an intro to probability theory too. But I just want to set some notation here for Bayesian statistics. So we're going to use the variable y for data that we observe, and we're going to use the variable theta for parameters that are unknown. So we basically divided our variables into knowns y that we observe and unknowns theta that we do not observe. The inference problem is going to be to observe a bunch of y's and see what we can learn about theta. To do that, remember Bayesian statistics is all probability based. A Bayesian model is a joint density, right? All a Bayesian model is something that tells you the joint density of y and theta together, right? That's it, right? Then we can do a whole bunch of stuff by just turning the crank on that joint density, right? So we have a sampling density. That might be the probability of observing the data given the parameters. We have a prior, which is the probability distribution over the parameters before we start. Right, and then the thing that we're actually interested in for inference the most is the, wrong button, yeah, but I went backwards, is the posterior, right? Our inference is going to be targeted at this. What can we reason conditionally about the parameters given the observation of data Y? And sometimes we worry about something called the evidence, which is the data marginal. And then I also want to point out that the likelihood here, people often call this the likelihood function. Technically, statisticians think of the likelihood is when you take this sampling density and think of it as a function of theta for a fixed Y, right? That's what the likelihood is. It's a function of theta for a fixed data set Y, right? We think of, in Bayesian stats, we think of this more like a sampling density where it tells us, given the parameters theta, how can we derive Y? We really think of it as a conditional distribution here, not just a simple function, right? It's a subtle distinction, so you don't need to worry about that. Everything we're going to do is going to follow through Bayes' rule. This is a very, very simple rule of probability theory. But let me just walk you through how this works, right? So the idea is we start with a joint distribution, right? We're interested, remember, in the posterior that's up here, right? That's the density of theta given Y, right? And what we have is our Bayesian model, Py given theta. Normally, we express that as the sampling distribution times the prior distribution, right? This is just the chain rule of statistics, breaks this down. So normally when we specify a Bayesian model, we specify these two things, the sampling distribution and the prior distribution. One tells us what we expect the data to look like given our parameters, that's the forward model. And P theta up here is what we know before we start, before we observe the data. We just encode all of our scientific knowledge before we start that way. Right? And now what Bayes did was say, well, look, we can rewrite that bottom using the law of total probability this way by taking an integral and marginalizing out the theta. Or we can expand it even further by taking that joint and expanding it with the chain rule. And now what we have down here is actually the full form of Bayes' rule, which expresses the posterior exactly in terms of the likelihood or the sampling distribution and the prior, right? And normally when we're doing inference, what saves us when we're actually doing numerical computation is that we don't have to compute this nasty integral for the evidence down here. This is the value of P of Y, right? And instead, we can just reason proportionally, right? We can just reason with this up to a proportion. So the denominator here does not depend on the parameters is the critical thing, right? So the denominator is just the density of Y, right? So the way people like to say this is the posterior distribution or density is proportional to the likelihood times the prior, right? That's the basic takeaway from the mechanics of Bayesian inference. And really feel free to like jump in and ask questions at any point. This should be relatively simple, but unless you don't know basic probability theory. This is a little more complicated. This is important, right? When we're doing Bayesian inference, everything we compute can be thought of as an expectation, right? What's an expectation? It's just an average, right? But they all take a particular form that's indicative of how Bayesian inference works. So if I look up here, let's say I want to estimate a parameter. I want to observe some data, and I want to say, what's my like best guess of what the parameter theta should be? Well, it's a conditional expectation of the value of theta given Y, which expands to this integral, right? But this integral is of a particularly easy form conceptually, which is that it's taking the posterior distribution, right, and averaging the value of theta over the posterior. That's all that integral is doing, is saying, give me the expected or average value of theta given Y. The reason we do this in Bayesian statistics, rather than taking something like, you may have heard of something like maximum a posteriori inference, where I would do something like maximize P theta given Y, or maxim, right, for theta, right? That's not a Bayesian inference method. Right? People in machine learning and the rest of the world tend to call those methods Bayesian, but if something involves Bayesian inference, it always involves integrating over our posterior uncertainty, right? So all of Bayesian inference takes our uncertainty in the parameters given the data and then averages all of our estimation based on that. The nice part about this form of parameter estimation is that it minimizes the expected square error, right? So unlike the map estimate, which doesn't have nice statistical properties, this one has the very nice property of being the parameter estimate that minimizes the expected error, the difference from the true parameter squared. Right? If you take the median instead of the posterior average, if you take the posterior median, that optimizes expected absolute error. Right? But it's much harder to compute, and people don't generally do that. In some kind of robust situations, people will. Right? But you can also do a lot of this in terms of medians, in which case this doesn't look like expectation calculations, it looks like quantile calculations, which are actually very similar computationally here. Right? So that's how we do parameter estimation in Bayes. But often what we're interested in is something called event probability. Right? An event in statistics is some subset of the parameter space. So for instance, I might be doing a clinical trial and have two drugs, drug 1 and drug 2, and I have the efficacy of those two drugs as parameters. Let's call them alpha 1 and alpha 2. And I might be asking, what's the probability, given my data, that treatment 1 is more effective than treatment 2? I want to ask, what's the probability that the value of theta 1 is greater than the value of theta 2 conditioned on the data? That theta 1 greater than theta 2 can be expressed as a subset of the parameters. That's what's called an event A up here, right? And when we want to do event probabilities in Bayesian inference, all they are is the expectation of indicator functions. Right? The indicator function is, are you in that event? So for instance, this might be, is theta 1 less than theta 2? Right? And when we integrate that, we get the probability of a given event. So this is what we use to do predictive inference, right? We want to know if it rains tomorrow, the probability is going to be, is it raining? Right? The event is going to be rain, right? And we're going to estimate the posterior probability. So you'll notice these are in the same form. Right? Both the parameter estimation and the event probability estimation, both are in the form of a conditional expectation given the data, right? Which we can do using the posterior, right? And then finally, we can do predictive inference. Like, say I want to guess what the value of something's going to be tomorrow, how many people are going to be infected with COVID next week, right? Well, that's going to be a case of predictive inference down here, where y twiddle, as I wrote here, y tilde, is going to be new data that we haven't observed. And this predictive, this posterior predictive distribution here is telling us, given the data we observe, what do we expect new data to look like, right? And this just marginalizes out the parameters of your model, right? But it's also an expectation. It's an expectation of the density of that new data given theta averaged over our uncertainty in theta, right? So there's two kinds of uncertainty that are measured here. This is a kind of sampling uncertainty, and this is our uncertainty about our parameters, right? So this new thing, there might be intrinsic variability, right? I might be rolling dice. Right? My predictive inference might involve some game of chance. There might be some intrinsic uncertainty there, right? And that's captured by this. The distribution of y tilde given the parameters may itself have some uncertainty in it, right? Coupled with the uncertainty of our estimation. Right? And again, please stop me if there are questions about this. Alex.
Yeah, sure, Bob. So you told us that you can, when you don't know the normalizing constant in the posterior, you can do everything you want, basically. Right. If you don't know it in this case, for these, what do? Do you just divide by the normalization of the posterior?
Oh, well, we don't ever need this. We only need the posterior.
Right, but if you, let's say you didn't.
Right. Do I have? I should have a slide for this. Here's the answer.
Okay. All right. We're gonna go.
Next slide.
I'll just let things happen. Don't worry. Yeah.
Oh, no worries. I'd actually rather get questions as we go along if people are uncertain. I like answering questions. Right. Here's what we're actually going to do for inference for this. So we want to compute these integrals, these posterior expectations. It turns out there's a plug-in way to do that just in general using sampling. So what I'm going to presuppose and not actually tell you about during this talk, even though it's what I do day in and day out, is we're going to be able to write Markov chain Monte Carlo methods that are going to be able to draw samples from the posterior, right? So we think of theta 1 through theta m as different random realizations of theta given y, given that posterior distribution.
I think we have a question here.
Okay.
Does Bayesian inference commute if you consider a set of evidence all at once versus considering it in sequence of batches?
Yes, is the answer. so that is what this is. This is like a standard intro to Bayes exercise where you do like a beta binomial distribution, and you can, if I had more time, I'd probably be doing that example as well. The idea is that you start with some knowledge, and let's say you're observing a stream of data. Like again, let's take COVID as an example, something I've been working on a lot for the last year, right? We're getting tests daily, right? Test information's coming in from all sorts of modalities, and every day we're getting new data. And the question is, how do we think of that in the Bayesian world? Well, the way we think about that is we can either take our model, take all of that data, and calculate some kind of posterior, or we can take one data item at a time. We take the first data item that we get, look at our model, look at the posterior that gives us, and then we take that posterior and use it as the prior for the next piece of data, right? And we can just keep chaining that, and that exactly commutes, right? Technically, though, it can be problematic because often you don't have a symbolic form for that intermediate version, right? So you can't often in the models we look at, you can't actually do that intermediate updating calculation. In special forms, it's all analytic, and you don't even need to do any MCMC. Things like Kalman filters that people use for like missile tracking, things that are just simple updates of preferences and things, that can all be done in a way where we can do very little computation. And historically, what's happened is people have focused a lot on models that have good computational properties. And I think what's changed in the last like 10 or 20 years is that now people are using much more flexibility in models because the computation's gotten much better. But what that means is we're using a lot of models where it's not so easy to do that chaining computation. You can do it approximately, right? But generally what we do is we recompute each time. Right, it would be nice to solve that problem. If somebody wants to work on that overall problem, that's a really good problem of trying to figure out how to make that more real, to be able to deal with the data one bit at a time. But anyway, the way we're going, were there more questions before I go on here? So we can generally do plug-in expectation calculation. So this is just like the bootstrap for calculating confidence intervals if you've done that in more frequent stats, right? The idea is that we're trying to compute the expectation of some function of theta given y. We can sample, and I'm just taking this on faith, that we can sample from the posterior where each one of those theta 1 through m is distributed according to the posterior. They may have correlation, but that's okay. This integral is going to work out to be the limit of this sum, right? Which is just f theta applied to the sample. So the idea is to evaluate this posterior expectation here, right? What I'm going to do is I'm going to average f theta over the posterior, and I can do that by averaging f over draws, right, mechanically. This is the big trick of Monte Carlo methods, is being able to do that. Right? And of course, we can't run m out to infinity in practice, so we have to use finite m, right? And this is approximately equal to 1 over m times this, right? And unfortunately, after Alex's talk yesterday, I'm sad to inform you that our error bounds are absolute, not relative, right? So this error that I'm talking about here is 1 over square root of m, right? So the idea is how many of these draws do you actually need? Right? Well, the more draws you have, the more precise your answer is going to be, but this is very slow convergence, right? It's not exponential, it's 1 over square root of m, right? Instead of going down, instead of the log going down linearly, the actual value is going down 1 over square root of m. And these are absolute errors, right? So you can think about these in terms of absolute errors this way. Imagine you were trying to estimate what the chance of winning a lottery was by buying a ticket every day, right? You keep buying tickets, your estimate every day is 0, right? Because you've just, unless you happen to win, in which case your estimate's way overestimated, right? So your chance of actually using something like random draws of lottery tickets to estimate how good the lottery is, you need a lot of draws, right? You can't do that yourself just by going to the drugstore. You'll never get a good handle on what the actual probability of winning is, right? You'll get reasonable error, right? Your estimate's going to be 0. That actually has pretty good error properties on an absolute sense, just not in a relative sense. Right, so 0 is really tricky, as people were bringing up yesterday. And MCMC techniques generally do not work real well for tail events, for extreme events. There's ways to get around that, but it's generally not a good method for that. You generally have to analytically compound things in to do that. You can't just sample tails way out, because you'd need a lot of draws. You'd need that capital M to get huge in order to do this accurately. Okay, so let's do a first example of a real backwards inference problem, a real inverse problem. This was actually the motivation. So I'm taking a great books approach to Bayesian inference, and we're going straight back to Laplace. So this was a problem that Bayes himself originally set up, but Bayes wasn't really a mathematician, right? So he couldn't solve the problem he set up. Right? On the other hand, Laplace came along. Laplace was a pretty decent mathematician. He figured this out. He figured out how to actually do the solution, and he actually applied it to the birth problem, right? So he had a data set that said, sometime in the mid-1700s, there were 251,000 men born, or boys born, and 493,000 girls born. Right? So it's like, what's going on? There's a lot more boys being born than girls. And Laplace wanted to answer the question, is it more likely that a boy is born than a girl? Right? Here's all this data. How do we actually answer this question?
Wait, you said total, right? N is total?
Oh, sorry. Yeah, N's total. Yeah, sorry. 493,000 total births. So fewer women births. Yeah, I should have listed the number of women births, but it's smaller than the number of men birth. So like, it's about 51% it's about 51%. That's still true today, by the way. So there's more boys early on, but then we die earlier. So the ratio changes as you go through time, right? So our model is really simple. Our model, the sampling distribution we're going to use is just going to be binomial. We're going to assume that each birth is completely independent and has a probability of theta of being a boy, right? That's what the binomial says there. Like I said, I'm not going to have time to go into all of these distributions for you. Though it is a good way to introduce math, because then you have to learn about the binomial coefficient and all this other cool combinatorics, and then the beta function. So we have the sampling distribution, which just says each birth is independent, right? This may be wrong. It may be that there's I don't actually know the answer here, but maybe there's correlation among families. Maybe they're not really totally independent, but often these independence assumptions are close enough. Then we have a prior, and Laplace just started with a uniform prior. He said, I have no idea what the ratio of boys and girls are. Usually when we're doing science, we could use a better prior than that, right? Laplace was not completely ignorant about the ratio of boys and girls. He knew it wasn't 99 to 1. He knew it wasn't 1 to 99. It was really just uncertain about whether it was, maybe 55 to 45 or, but it wasn't super extreme. So normally what we'd do in real applied problems is we'd put more information in there because we knew a little bit more going in than we actually coded, but I'm doing this straight the way Laplace did it. Right? It turns out then that the posterior is something called a beta distribution. So Euler wrote something called a beta function. It lets you actually solve this thing analytically, which Laplace figured out how to do. And there's a distribution that uses the beta function, Euler's beta function, as a normalizing constant. The beta function is essentially a distribution over probabilities. And the first argument is the number of successes and the number of failures that have been observed already. And then we're looking at what, this is all very complicated. If you're not used to thinking about that, forget I said that. The posterior, Bayes was able to work out to be this analytically. He didn't need to do any sampling or anything, right? What we get, so the way we like to talk about reports in Bayesian statistics is not with an estimate, not to say, well, my estimate of theta is 51%. But rather to phrase things probabilistically, right? And phrasing this probabilistically, you can say the probability that theta falls between 5.08 and 5.12, like 51.2%, is 99%, right? So we're pretty sure that it's in that interval, right? But then we can also calculate the event probability, right? What's the probability that theta is greater than 1/2? That is, there are more boys than girls. It turns out to be a really close to 1 number, right? So what Laplace wrote is that he was morally certain that there's more boys than girls being born, right? But he did that by turning the crank on this example, right? Luckily, nowadays, right, the people used to say that to be a statistician, you had to be part mathematician. Nowadays, to be a statistician, you have to be part computer scientist, because we tend to do all of this stuff for much more complicated models where there's not actually any kind of analytic posterior we can do. And the only way we can solve these problems is with sampling or some other kinds of approximate inference. Sure.
Questions. First, the morally certain thing is in some sense a statement about a tail event.
Yes.
And what really goes into that, and is there a way to assess how good it is? I mean, is there some kind of Gaussian distribution at the back of this which is really giving you the 10 to the minus 42? And if it was important to me whether it was 10 to the minus 10, is there some way to do better?
Yeah, so that's a bunch of questions rolled up together. Here, what we're doing is we're actually taking this model, right? So we're actually looking at this sampling distribution. So these inferences are all conditioned on my assumptions. And my assumption is that each birth is independent, and each birth has a probability theta of being a boy. Given those assumptions, we know that the distribution over thetas given data follows a beta distribution. So we can just work that out analytically, and there's not a way to get a better answer than this.
Okay, but this is in a sense, this is therefore contingent on the binomial statement at the back of which is some kind of Gaussian, and you're really looking at Gaussian tails.
It's not Gaussian, it's a beta tail. But you can transform it and it looks like a logistic distribution, but roughly speaking, yes. Yeah.
The second question is, as you said, the assumption here is that there's no correlation.
Right.
Suppose that I wanted to test the hypothesis that there were no correlations. Is it easy to explain in this language how I would do that?
Yes.
You assumptions about the pairs in the sample.
Right.
How can I see if it breaks?
So typically what we do in that situation, again, this is different depending on what kind of Bayesian you are. Traditionally, what Bayesians did, they would do one of two things. They would either force themselves to write what they call reference or objective priors that don't have any or very little impact on the data, and then they just trust the results because now we're doing frequentist stats. I should point out as well that this is exactly the same problem in frequentist stats as in Bayes. Like Bayes gets a lot of flack for having priors, and people are like, oh, why do I have to have a prior? It's so arbitrary. What everybody's forgetting is that the likelihood is arbitrary, and it has a lot bigger impact on inference usually than the prior, right? So if I was doing this in a frequentist setting, I'd be making the same kinds of assumptions, but it's really important, this is a really important point, that our inferences are conditioned on our model assumptions. So we want to go and test our model assumptions, right? The way we normally do that is we compare, well, we can do it in a bunch of different ways, which I won't have time to go into. What we like to do first is something called posterior predictive checks, which looks at our posterior inferences and see if they're consistent with the data. So what we do is we generate posterior samples that correspond to ways the parameters could be. From those parameters, we simulate data. Right? And then we compare the data that we simulate with the data we actually started with in terms of things like tail statistics or means or medians or, skewness or whatever we care about to see if we're capturing properties of the data we care about. Right? So normally in a regression where you'd look at correlation is you'd plot something like residuals, like say you were doing a time series of like financial returns or something, and you'd have some predictions and then you'd have some actual observed things, and you'd look at the discrepancies and you'd just usually eyeball them and say, are they actually normally distributed, or is there some kind of trend here, some kind of what people call heteroscedasticity in econ. It's the only one of those words I can pronounce, so I like using it when I can. But I always have to go look up what the economists mean by all these words. But if the distribution of your errors isn't uniform, then you've got to go back and do modeling. So we like to think of this as in a loop, where we build the model, we test the model's results when we're done, see how well they fit, and if they don't work, go back to the drawing board and rebuild new models. This is really considered forbidden in a lot of statistics, to go back and like see the data, then go back and fit your model. So in some sense, I think the pragmatic Bayesians are much more like machine learning people. We're much more like, let's go and get a model that works, right, and apply it, rather than trying to do some kind of hypothesis testing, right? But very important point. All of our inferences are conditioned on models. And Bayesian inference is nice in that we're guaranteed to get the right inferences according to probability theory if our model's right, right? But usually our models are not right. So personally, I work on a probabilistic programming language called Stan, right? And I just wanted to show you what this model would look like coded up in Stan. So the way Stan works is you declare your data, right? Here, we're going to have y for the number of boys, n for the number of total. We have a parameter that's constrained to be between 0 and 1. We have a uniform prior on that parameter, and then a binomial modeling distribution. And then we have indicator functions written down here for theta greater than a half, right, and simulation, right? Those simulations, that's how we code these two things on the bottom here. Right, one's the indicator function for this, and one's the indicator function for that, right? Or no, one's actually simulated data, sorry, and one's the theta greater than a half. So sorry, that's backwards. So the theta greater than a half is the second one. I didn't actually do the first one on this. Right, so if we actually run this, you know, we code that model up, we run it, we print out the posterior, right? It gives us an estimate of the posterior mean, a summary of the posterior mean, a summary of whatever intervals we want. Here I've asked for the posterior central 99% interval, and we typically get some standard error, right? So the estimates, the posterior sample mean, the 99% intervals estimated by quantiles, the probability that theta is greater than a half is that indicator which rounds off to 1 because we're doing floating point and we're doing Monte Carlo sampling, and Y sim is a forecast for the next 100 births. Right? And that forecast comes with uncertainty, right? We're going to do the next 100 births. We expect them to be somewhere between 38 and 64 boys, right, given our uncertainty. The reason this number isn't 51 up here, right, is because of the sampling uncertainty, right? Even if we know theta, there's still uncertainty in who's actually born. Right. Okay.
Bob, so I have a question. So are you doing there in Stan Monte Carlo, or are you simply solving it analytically?
No, this is using Hamiltonian Monte Carlo.
Okay. Yeah. And you do it just because you want information of the sampling uncertainty, or like why?
No, just because generally what Laplace did doesn't work because you can't actually work things out, and this is just like a hello world simple example of how Stan works.
Thank you.
Yeah, if I actually had to solve this problem, I would do it analytically, right? But generally our models are a lot more complicated than this, as you'll see from the next model. So what is our workflow? And this is getting back to the earlier question, right? We typically design an experiment and collect some data. Then we try to evaluate our model. We do prior predictive checks to say, is the prior sensible? We generate some data according to our prior and say, is it generating reasonable things? Are the assumptions going in reasonable? Then we do something called simulation-based calibration. We simulate data according to the model and make sure that our algorithm can recover it with the right coverage. Right? That tests whether our algorithm works for data that actually comes from our model, right? Then we start wrestling with real data, right? We start looking at posterior predictive checks that says, does the model capture aspects of our real data? Like maybe there's correlation in our real data that our model's not capturing, and we can find that out by doing posterior predictive checks. Right? And then finally, we do holdout evaluation or cross-validation, right? We build our COVID model and we predict how many deaths there's going to be next week, and then we wait and see if we're right, right? And then we try to adjust our model because, you know, we get things wrong, right? And if the model's lacking, we tend to improve the model and repeat step 2, right? And if the data is lacking, we often have to collect more data and repeat step 1 as well, right? There's a paper that I and like 10 other Stan developers are busy turning into a book that's about 2/3 of the way done. I actually am optimistic it will get done. That's all about Bayesian workflow and how we actually fit problems, and goes through all of this stuff in gory, gory detail, which I won't have time to do in this talk. right? But often we're interested in models that are calibrated. What we're looking for is calibration in the sense that if we say there's a 75% chance of an event, there really is a 75% chance of that event. Not a 95% chance, not a 50% chance, right? So calibrated predictions, right, depend on how much data you have. I'm not going to be able to go into this a lot either, right? There's whole, like, it's a whole seminar just to talk about calibration and statistics, right? But the idea is in Bayesian statistics, everything's about probability, and we want our predictions to be well calibrated, right? We want to be able to trust our probabilistic predictions and act on them, right? If we're doing something like running a betting pool, we better do that, or we're doing finance, or we're going to lose our shirt. Right, and we often want sharp predictions. So given two different predictions, like we want intervals that are tight, right? So we'd rather know that alpha is in 58% to 59% than it's somewhere between 50 and 60%. We might have two different models, both of which are calibrated and that the probabilities are right in some sense. But we like the ones that are sharper better, right? And similarly, probabilistic predictions that are closer to 0 or 1 are sharper. Right, so this is sharpness is an entropy kind of notion. How much entropy is there in your predictions, essentially? Right, and then what we want to do for probabilistic forecasts is we want to maximize the sharpness of our inferences subject to calibration. Right, and the nice part about Bayesian models is that if they're well specified, they're well calibrated in most cases. Like it depends on the actual structure of the model and the asymptotics and whether you have parameters that vary with the data, but generally, models are well calibrated if they're true. Unfortunately, when we're dealing with hard scientific problems, often our models are not true, right? Even if we think our physical model's right, our measurement error model of how we get the data is often a generalization. We might assume we're weighing something with a scale that's unbiased and has normally distributed errors, which is probably not the way your scale actually works. So I guess I've got 5 minutes, which will probably be about enough to go through the last example I have here. This is a real example. I mean, not a real example. This is actually like the hello world example from solving ordinary differential equations. And I thought I'd talk about how we do that in something like probability theory. So Volterra, back in 1926, had a model of predators and prey. Right? So we have populations at time t. The variables we care about are the number of prey and the number of predators, right? And Volterra wrote a couple simple differential equations wrote a simple like set of differential equations here for this that govern the change in the populations, right? So you can find like 20 tutorials for this in Intro Applied Math. It's like the standard textbook example of how to solve ODEs, which is why I used it so I could check that Stan was getting the right answers. Right, so basically we have 4 parameters to this model. One is the unfettered prey growth. One is the shrinkage of the prey based on the size of the population. So the larger the population of predators is, the more downward pressure there is on the prey. And the predators are exactly the opposite. Unfed, left to their own devices with nothing else, the predators are going to die off. And there's also going to be predation growth. The predators, if there's a large amount of prey, there's going to be more predators available, right? So it's a very simple dynamics model. And if you go back to the original Nature paper, I love these old diagrams. This was like Volterra's diagram from 1926 of solutions to this, right? So we've got the predator and the prey on the 2 axes, and time goes around like this, right? So this is the dynamics of the population. Right, so these are plotting out times, right? And those omegas are different possible solutions for the parameters that he was talking about, right? So we'll go and plot this a little more.
That's so weird that those 2 loops cross, because I don't think solutions are allowed to. Curves are allowed to.
Having the usual problem with going backwards and forwards. What?
Solution curves aren't allowed to intersect like that. So
well, these are for different values of the parameters. These are simulated solutions for 2 different sets of the parameters.
2 different sets of parameters. Got it.
Yeah, I should have said that. Yeah, these omegas represent the parameter values, I think, somehow. Or at least maybe those are just the posterior means. Damn it, this is so hard to control with the. I can see why everybody's failing with this in real time, because there's a different button for going back. It's not the usual like rocker panel. So knowns and unknowns. The knowns are the number of pelts collected at each time. What we're going to do, I'm trying to go fast and of course failing. What we're going to do is we're going to have data, which is the number of pelts collected at the Hudson Bay Company. I thought I had a plot for that in here, but maybe it'll come up. Our unknowns, so we don't actually know the population size. We can't actually measure the population size directly, but we can measure the number of pelts we have. And the unknowns are all of these parameters, right? The measurement and model error is very simple, right? We're going to take that differential equation, and that's our forward model. If we know the parameters, that's going to predict the population size. Now all we need is noise terms, right? We're going to assume that the error in our measurements are log normal, which means that the errors are going to be proportional to the population size, right? And normal errors are additive. They're like value plus or minus a value. Log normal errors, log normal values are always positive, and they're times divide errors, right? Rather than plus or minus errors. Right? And then we're going to have some weakly informative priors that determine the scale. We're actually going to fit the sigma 1 and sigma 2 here, right? And then we're going to take some weakly informative priors that simply determine the scale of the problem, right? So the reason these are at different scales is the beta and deltas have the two populations multiplied together, whereas the alpha and gamma parameters are just straight up parameters. So they wind up being on different scales in the prior. And similarly, we take priors on the sigma values, right? The assumptions are that pelts are a reasonable proxy for the population, and the population only depends on the predator and prey sizes, right? This is a very dumb model of population ecology, population dynamics, because it doesn't take into account weather. It doesn't take into account how much grass is growing. It doesn't take into account disease or all sorts of other things. Right, and we know the rough scale of the solution ahead of time because we roughly know like how many of these things are there. And the measurement error we're assuming is proportional to the population size. Right, and I'm not going to go on the normal and log normal. So sorry, I meant to do this first. There's the lynxes, there's the hares. It turns out that lynxes eat almost exclusively these hares. The hares eat all sorts of stuff, which is why they grow even if there's no predators around. But if there's no prey, the lynx die out because they don't have anything to eat. This was the original data collected from like the 1850s up through like 1920 or so. Luckily, somebody transcribed that. So if you actually plot this data, here's the plot on the right is the way Volterra did it. The plot on the left is just the actual plot of the populations. And you see that the lynx population size lags the hare population size, and it just keeps going like this, right? So presumably this is what Volterra did. He looked at this and said, this looks like a harmonic oscillator. Let's build a standard kind of spring model for this whole thing, and off he went, which is kind of how we do a lot of this stuff, right? So, but remember, the model's actually predicting the number of pelts, and we're making an assumption about what it does. So we can write the differential equations up in Stan, and then we just apply this integrate an ordinary differential equation function, which generates our solutions. And then the measurement error, the measurements we actually get are based around the solution. So this UV hat is given the parameters that we have, the solutions to U and V, the population dynamics. This is the time trajectory that we're getting from the differential equation given all of our parameters, right? And then what we're assuming is our actual measurements have some noise around that. That's multiplicative, that's based on the size of the population, right? So then we can plot out what the answer is. So what I've done here is I've plotted the measurements, which are in red, and the predicted values, which are in blue. And I continued the predictions past where we have data from. And I could keep doing predictions, 10,000 years into the future, but no one's going to want to trust those, right? Because we expect there to be external shocks and things like this. I think this data set was very well cherry-picked to be the hello world example for a reason, right? And what this is plotting is 90% posterior intervals around there, our uncertainty in that. So we can see that the model's roughly capturing what's going on, but there's, problems here, right? There's things that look heterogeneous compared to the nice smooth trajectory that the model, and that can come from, maybe the hunters were having trouble that year, who knows? Sure.
Point out where the unknown parameters are that you're calculating the posterior of.
Yeah, so theta. Right, theta is the set of all the parameters, and those wind up getting packed in. So that's the alpha. So yeah, so sorry, theta is the alpha, beta, gamma, delta thing up here, and those wind up getting unpacked. Yeah, this defines the differential equation. Exactly. So in other words, the differential equation is just like the multiplication in a linear regression, right? The differential equation's picking out the expectations, and then we're modeling error around that.
And why aren't the initial values of u and v at time 0 also packed into theta as unknown parameters?
They are. They are unknowns.
They are. Okay.
They are
all right. They're also there.
Yeah.
Okay.
Yeah. We don't take. People often hack this and they take the initial measurement, say, as the initial time, but we did it right. So yeah, the initial conditions are unknowns, right? And here's some predictive draws, right? That is, I just take draws from the posterior. This is like my posterior predictive inference for what I think the populations are going to do, right? And they don't look smooth because they're measured at time, yearly intervals. Right, so there's a lot of uncertainty as to where this population is going to go from this model, despite having like thousands and thousands of pelts that it's based on. Right, I don't think I will go through identification of parameters, which is really important. But let me just summarize before jumping into general questions. So we start out with a mechanistic forward model of the dynamics. Right, so this is going to tell us what the predicted populations are given our parameters. Right, then we're going to put an error model on it, which says, okay, my observations are noisy. I'm measuring pelts collected by hunters, not the actual population. There's going to be errors in that, right? We're going to add some weakly informative priors that roughly fix the scale of the answer, and then we're just going to turn the crank with Bayes, right? This is like, this takes like, you could build this model in Stan in like 45 minutes. You probably couldn't because you'd need to look up what all the functions do. But like once you know it, this is like a really easy problem. And people use this for many different kinds of scientific models. So for instance, we do a lot of pharmacological modeling where we'll model patients, right? And there's a differential equation for the pharmacokinetics of how the body clears the drug and what the concentration of the drug is in the body. And we'll let each patient in the clinical trial have slightly different metabolic parameters, right? And we'll be able to solve all those differential equations, and then we take measurements. So for instance, one of the big clinical trials we did was for a macular degeneration drug that inject things into people's eye every month. And we were doing a trial of, could you inject it every month instead of every week? Don't get macular degeneration. You get injections in your eyes. And there, the noise was because the data we were getting was they were reading an eye chart, right? So the data we were getting on how this was affecting their disease was they would read 100 letters off an eye chart, which is super noisy, right? So there was noise in that process. Right? So I also do this for like soil carbon modeling. You can model a compartment model of soil capture and respiration, and it looks just like this Lotka-Volterra model with slightly different differential equations. Right? People are doing this for physical models of all sorts of things. Okay, I'm not going to get into, I thought, as usual, I thought I would race through all of this and be done and have like, I have like 10 more slides for when I got through the presentation 15 minutes early, but instead I will turn over to questions.
Questions.
It's like a jazz.
And remember to use
like
your mic.
Snapping. Oh man, I've only got 3.5 minutes of penalty time. Dave,
When I push the button.
push the black one down until it pops up.
Can you tantalize us with one or two of the slides from this section of your talk?
Okay, well let's see if there's other questions before going on and blasting people with. Okay.
Sure. All right.
Okay. Sorry. I will at least drop this out. Right. So AI is really about thinking, playing Go, driving a car, that kind of stuff. It's not really about a technique. Like if you look at Google, they call regression, and the European Union starting to regulate AI. They literally include like just linear regression as a form of AI, right? So it's it's basically anything we do to interacts with humans, right? Machine learning is much more difficult to characterize. Traditional stats focuses on data analysis, but machine learning much more on prediction. right? And I think that's why machine learning is completely eating the lunch of traditional statistics, which typically doesn't do any prediction, right? They typically fit models, analyze data sets, and then declare success and go on to another data set. Whereas machine learning came along and said, we can actually do something with statistics, start making predictions. This was standard in Bayes, but not Bayesian stats isn't widely practiced compared to sort of more traditional stats, right? It's getting more so, but Bayesian stats is about data analysis and prediction, right? So I think you can do this both. The problem is trying to apply Bayesian statistics at a machine learning scale to do something like self-driving cars is really challenging, right? So Dave's going to be, and as an intro to the next talk, Dave's going to be telling us about some approximate computation methods to this that lets this scale much better than something like Monte Carlo methods do, right? So in terms of models, stats tends to focus on interpretable, tractable parametric models, whereas machine learning tends to focus on black box, kind of intractable, non-parametric models, giant over-parameterized neural networks with non-linearities in them, right? In terms of inference, machine learning tends to focus on point estimates. You tend to find like a maximum likely, try to find a maximum likely estimate, although most machine learning problems don't actually have well-defined maximum likelihood estimates that anybody can find. So we have to do that approximately as well, whereas traditional stats focuses much more on estimates, confidence intervals, and hypothesis tests. Bayesian stats tend to focus on calibrated posterior uncertainty, and it uses probability for everything. So we can do the same sort of task that machine learning do, except we'll do it probabilistically. We won't say, yes, I think this is a cat. We'll say, I have a 92% chance of this being a cat. You can do that with a lot of machine learning models, but they tend not to be very well calibrated. So there's another whole research industry springing up trying to take the deep learning models of machine learning and sort of put a calibration layer on top of them, which tends to then look much more like traditional statistics. I think that was it. Oh no, scale. ML tends to focus on really big data, whereas stats tries to squeeze a lot of information out of small data, right? And the problem is you want to think about small and big data carefully, right? You might look at Amazon and say, Amazon's got huge amounts of data, but they don't actually have that much data about any individual person, and the data they get's super confusing because I buy presents for people and my wife and I share an account. It's a really complicated problem, and they don't actually have enough data for what they'd like to do. Right? So they have to use statistical techniques to try to squeeze more information out of that, right? And ML models, on the other hand, tend to be more flexible and also scale with data better, right? So stats, I think the real interesting research question is, I think as we get more data, how much more model can we build? I think that's really the big pressing question. But I think I'm now out of time, actually.
Yeah, we'll take a question from Zoom. There's a Python library called SymPy, which allows users to construct algebraic expressions using Python expressions and apply algorithms to solve systems equations using these expressions. Is there a variant of Stan which allows these sorts of manipulations?
So I didn't catch the name of the package or what the manipulations were.
SymPy, and it's doing...
Oh, no, we don't have anything like that built into Stan, but it's the kind of thing you can use on the outside to build a Stan model, and people have done that, right? But normally, no. Normally we use just automatic differentiation for everything. Okay. Can we take one from somebody who's not Alex? Sure. Want to take a last question? I'll see you all the time, so.
Yeah, from the back.
Actually, is there a sense, one can do the whole formulation in CDFs, like cumulative distribution functions, rather than densities. Yeah. And what's your impression of where is it advantageous?
Well, the nice thing about CDFs is they unify discrete and continuous distributions and then mixed distributions like spike and slab things. So from a theoretical perspective, like everything's done with measure and CDFs. Like when you get serious about this, that's where all the math goes. Right? In practice, it's much easier to deal with densities. Right? The problem that you run into with densities, much more so in classical stats, but even in Bayesian stats, is they depend on their parametric forms. Right? So often the way you parameterize a problem will affect the maximum likelihood solution. It tends not to affect the Bayesian solution you do this. So you have to be careful when working at densities because you really care about probabilities, and densities can be very confusing about that. Like densities have these properties, like if you look at a multivariate normal, right, you look at the mode and everybody thinks all the samples are going to be around the mode, whereas in fact there's so little volume around the mode, there's almost no samples around the mode. Right, so I think the intuitions you get from extrapolating densities into higher dimensions are all wrong for most people, so it's tricky. Right, but I've never seen anybody try to do this kind of thing directly with CDFs, so is the answer.